first one we're going to go through, hopefully you can get there. Yeah, okay. So if you click on, open this up in a new tab. Click on this HTML1. This takes you to this lab here. So this lab is going to feel very different than what Mark has been talking about the last 2 days. But we need to introduce this now because it's the foundation for what you're going to see starting second lecture next week, and then the lectures out after that when they start to become multivariate. We're going to work a lot with matrices, and you're going to need to be able to write models in matrix form so that you can specify them for the software that we're going to be using. And also when we give the lectures, when we're writing down multivariate models, we're going to write them in matrix form. So this lab will start with something that is familiar to you, which is linear regression, and show you how to write linear regression in matrix form. So this is just pedagogical to get you used to thinking about models in matrix form. So if we look at a simple linear regression, the form of that is that, let's say it's this regression right here. So this is the R code for a linear regression, and it's going to regress this data stack loss against this variable airflow, which is in this data set DAT. And if we look at DAT, I think I have that on the previous page here. Yeah, you can see what this looks like. This is just the first 4 rows of this. If you run this code and then this code in R, which you should do that, and then you run DAT, you will see this. To run this code, you can either copy and paste this right into your console, or if you go up here, okay, so if you're on that page and you go right here, it's going to take you right to the R Markdown file for this chapter. And then you can go ahead and, can you just download that? You can definitely copy and paste the whole thing and then just run all that code.
I think for us, because say we work it, we're not administrators, but
yeah, so that's why I was saying, you know, maybe it's easiest just to like copy and paste it. So
there's a link up there to the base of our script, too, not the markdown right there, here.
yeah, so you can go here and then you're going to get it's not going to have the text, it's just going to have all the R code. So that actually might be the easiest way to go. Just download that and work from that. Okay, so what this means is that we're modeling stack flow, the ith value of the stack flow, as a function of an intercept, error times some weighting plus an error term. And in this simplest format, we're assuming that the errors are independent and identical. So we don't just have one data point, we have many data points. And we can write that as a matrix. So let's say that our whole data set were just 4 data points. And so that linear regression is this right here. So what we're saying is this is a matrix. It has 1 column and 4 rows. This is a matrix. It has 2 columns and 4 rows. This is a matrix with 1 column, 2 rows. And here are errors, 1 column and 4 rows. And when you do the matrix multiplication, this kind of goes on its side, and you're going to multiply the alpha times 1, and then the beta times error 1. So then you see that stack loss 1 is equal to the intercept plus error 1 times beta, and then the next one is intercept plus error 1 to error 2 times beta, and this one error 3 times beta. So that matrix equation there, like I said, this is matrix multiplication right here. That is this model right here, but for all the data points. And this form right here is what you're going to start seeing end of next week. A little bit of end of next week. Definitely by week 3, we're going to be writing models a lot like this. We can write this more succinctly like this. So this is Y is our data, and notice that it's bolded. That indicates that it's a matrix. That's a standard convention. And that it's a lowercase is the convention that it is a column matrix. So that means it's just 1 column. And then the Z, this is this matrix, and it's an uppercase, so that indicates that it's not necessarily a column matrix. In this case, you see it has 2 columns. So that's the Z matrix. And this X here is that here, and this is your column matrix here. Okay, so this is our data. And in this format, the X are our parameters, and the Z are our covariates. So the error and the 1 for the intercept. And this form of a linear regression happens to be how the LM model is set up. And you can see that by, if you were to run this fit, and then you were to ask it, tell me the model matrix. So just ran that, and then if you looked at the Z here, you would see it's this thing right here. This is just one way to write this model. It happens to be the way that LM writes it. And then this part is it's an aside. You don't have to know how to solve for these things at all. The point is that once you have this, you can then do some matrix algebra and solve for the Z. If you were to kind of plug, you go through that, you come up with this equation here, and this is your solution for the X's, which are your parameters. And you could write a little bit of R code and define that Z. Okay, so you're going to make a Z that looks just like that. It's going to be a matrix with 1s and then the airflow here. You're going to make another one that's going to be your Y, which are your data. And then if you ran this code here, so here is my Y. If you run this code and you look at what that Y is, it's a matrix with 1 column. It's got our data. And then you set up your Z. It's going to be your 1s. And then it's going to have your airflow. And then if you just write that equation there in R code and solve, which is the inverse of the transpose of Z, matrix multiplication times Z, and then matrix multiplication times, again, the transpose of z, matrix multiplication times y, and you get this. If you looked at the coefficients that you get from the linear regression, you see it's the same thing. What if we had more variables? So we didn't just have air, let's say we had air, water, and the acid. So those are the three covariates in this data set. And now if we did a linear regression and we said stack loss is a function of those three things plus an intercept, now the model looks like this. So stack loss 1 is, again, we're going to kind of think about kind of rotating that. We have our alpha plus beta 1 times air 1, beta 2, it's a different beta times the water, and another beta times the acid. That's what one's going to be, and then it's going to do the same thing for the next one, etc. And again, if you were to go in R and you were to fit that linear regression, did I do that up there? I think I did that up there. Yeah, right here. Yeah, it's right here. So if you run this code and you fit that, and then you pull out the model matrix, you'll see that it is creating that matrix right there. Here it is, right there. And you can do that same bit of code where I solved for the coefficients. You can set that up again, you solve them, and boom, here they are, and you can see the coefficients that you get out from your linear regression fit are exactly the same. All right, so that's one way you can write that model. When are we going to see this form? And when I say this form, what I mean is we have covariates. This is things we measure appearing in this matrix. And then we have parameters over here, and we have data over here. That form is going to come up when we do dynamic linear models. So in a dynamic linear model, it's like a linear regression, except that the parameters, like the intercept or the slopes, those are varying in time. And so in that model, it's going to look a lot like this. We're going to set this up, and then this is going to have a little t next to it, because this part is going to vary through time. Okay, I'm going to let you go through this on your own. Well, I'll mention it briefly what's going on here. So if we took the transpose of form 1, we get another form that would look like this, where we have our data, and now instead of a column, it's a row. And then we have our parameters over here as a row. And then we have our covariates here, and now they're appearing in rows instead of in columns. If we did the matrix multiplication, it would work out, it would still work out, it's still the same linear regression, we've just kind of switched things around a bit. And now we can take this column, we multiply it by that matrix, so we get stack loss 1 is equal to the intercept, air 1 times beta 1, wind 1 times beta 2 plus beta 3 times acid 1. And that's the that linear regression model again. It looks really different, but it's just we've moved things around a bit. It's still the same model. And we talk about, oh, okay, wait. Yeah, so that Oh, I didn't talk about when that form shows up. This form where we have parameters on this side and our covariates over here, this is going to, models are going to look like that in later on in the course where we have covariates in our multivariate models. Okay, here is yet another way we could write that linear regression. Now we have all our covariates in one column. There aren't multiple columns, just one column like that. And we have all our parameters over here, but now we have a bunch of zeros appearing in different places. So let's see how this is still that linear regression model, the first one. So we have the stack loss 1 is equal to, let's take this, and we're going to multiply it like that. And so we're going to have our intercept times error 1 times beta, and the rest of them are going to zero out. So stack loss 1 is alpha plus beta times error 1. That was our model. So stack loss 2, same thing. We just sort of rotate that, and we have our alpha. This one gets zeroed out, and then we have our error 2 times beta. So it's that same model. This form is what you're going to see mostly in weeks 3 and 4. It's going to appear like that. And let's imagine we had more explanatory variables. Let's say we have the 3, and now things start getting really big. So now the Z matrix looks like this, and like imagine we had this over here, and we're going to multiply it. So now we have that long column. We kind of flop it over and we multiply it. So the first row is going to be alpha times 1, and then beta 1 times error 1. The next 3 get zeroed out. Beta 2 times water 1. The next 3 get zeroed out, and beta 3 times acid 1. And then for the next row, you have to shift things over so you get the ones that correspond to the second data point. So now let's go back here. What you're going to be seeing when we work with these covariate models is that when we write things out like this, like a matrix, it's really easy for us now to put constraints on our parameters. So what if we wanted, for some reason, we wanted all the effect of air and the effect of water to be the same, but the effect of acid to be different. Then what we could do is just say, oh, okay, fine, that's easy. We'll just make this a beta 1 also. So this is beta 1, these are all beta 1s, and these are different. These are beta 3s. So now by writing a matrix form, we can very easily put that kind of restriction on. Or we could make things as complex as we want. Maybe we'd say, well, I want these two to have the same effect of air, and I'll make these beta 1b because I want them to be different. But these, I'll leave these all the same, all 4 sites. And in this one, I want these two to be the same and those to be different. And we can easily specify that by just putting different subscripts on here. And what you're going to see when we start working with multivariate models is we'll start putting those kind of constraints on. So these 4 rows might correspond to measurements that are taken in different regions. So one's in the north, one's in the south, and that's why you want to impose something like the effect of air is the same in the north or the same in the south. Okay. Great. Okay. So So what we'll do is give you, how much time do you think? 20 minutes? Just kind of plug through this and start working through. I think 20 minutes should be good. That'll at least get you started. You should run through all that R code, make sure it kind of works. You kind of understand that, and start skimming through these other examples. And all of them, it's kind of the same idea. And then what you'll do after that, I just want you to go up through about, up through section 2.5. This will show you examples where you have effects of different regions, how you might set that up, how you could set that up with matrices. So starting getting used to kind of setting up matrices like that. You can ignore the seasonal effects. That's getting kind of complicated. You're welcome to go through that. You'll learn some more, but you don't need to do that for this course. And then for the homework, you'll go through these problems, but not all of them. Before you start your homework, make sure to look here and look at the ones that I've written out. I think we're going to add a few more problems, I think, of some time series functions, but we haven't completely decided. But these are the ones that you work on from the linear regression. Okay. And remember, when you do your homework, go ahead and use that R Markdown template. That's also going to show you how to make it'll show you how to make matrices the way that I did it, because it's going to ask you, okay, I want you to write this model out. You need to write down that matrix. If you get hung up on writing out a matrix so that it appears the way that mine appear here, so right. It's going to show you examples of how to make this kind of math appear. And if you run into trouble with that, don't waste your time. This is not a course about how to write matrix math so it looks beautiful. Just go ahead and write that in the R code and we'll be able to understand. We just want to make sure that when you're asked, okay, I want you to make that matrix, I want to make sure that it's a matrix with 2 columns, 4 rows, and the ones are in the first column and the errors are in the second column. Something like that, okay? Okay, so go ahead and run through that code for 20 minutes, and then Mark will take you through the next lab.
No.
Wait, should I take a minute to turn this off? Pause.
This conference will now be recorded.
Wow. Good news. Okay, so what we're going to do, you have to mute yours. Got it? All right. For the last bit of lab here, we'll start through this. We'll get through about 2/3 of this chapter, probably, on the intro time series functions. And then I think what we'll do is Tuesday, at the end of lecture, we'll finish today's lab. And then what I would suggest you do, and we'll remind you on Tuesday, is start that bit of the homework so that you have a couple of extra days to work on it before next Thursday's lab, where you'll then get more. So next week's homework is going to be a bit robust. Today, well, this week, you just have the matrix algebra problems to deal with, and then, yeah. Okay, right, let's see here. Sorry, I also need, Okay, so what we're going to do today is go through the first bit of chapter 3 here, and it says, here, let me make this a little bigger. Right here, it mentions that you can load these data files, and I think you should be able to do that. If you, I would have to click those links to save them, and the reason why is, much to my horror, you can't download them right now because they're NOAA websites. Oh my God, like who does that? If you try this right now, you're gonna get something. Oh, it's closed, shut down. Someone's still paying the electric bill anyway. And so it's good that we have them because otherwise it would be very difficult to complete the rest of the lab without them. So if you want to follow along, you'll have to, load the data from our data files here. So you'll have to download those to some directory and then load them appropriately. The phytoplankton one you don't need now. That's for your homework assignment next week. But if you want the CO2 and the temperature data, that's the best way to go. Okay, so what I'm going to do is I'll flip back and forth here between this book and an actual script. So let's pretend we have these loaded. The first thing we want to talk about in our TS objects. So I think I mentioned earlier that there is an actual object just like matrix or integer, that sort of thing, called time series object. And the nice thing about time series object is that they carry around a little bit of metadata for you that you don't have to deal with. And then when you do things like plotting, it will play nicely. And you can do some other things once you've done them. This function, TS, is how you create a time series. And it has a few arguments that you need to do. The first is you have to tell it what you want to turn into a time series. So typically it's a vector. Then the other is this bit about frequency, and what they mean by frequency is 1 over the frequency. They mean the period. So if you had monthly data, most people would think of the frequency as 1 over 12, but what they really want you to specify here is 12, not 1 over 12. So that's the first thing to know. And then the other is that there's a start element which tells you where you want the time series to start. If you have annual data, you can just put in a year. So start would equal 1991 or something like that. If you had a year month, it would be something like 1969, comma, the year it actually started. Okay, so that's how you do it. So basically, we can do that with a time series object. I'll click back over here. So load these things. Oh my God, my screen is so small. Okay, so I load them and then we're going to plot them. So here's where we created this time series object here. And here's the plot of that time series. So this is that function plot.ts for time series. So you don't have to give it an X value, you just give it the Y essentially, because it knows something about, so here it even knew to start this in 1959, and so it'll fill in the axis appropriately. You'll have to add your own labels and that sort of thing if you want them. Okay, so we've also got a temperature time series, and we can plot that if we want. Oops. What did I do wrong here? Oh, this. Okay, I know what I forgot to do. There. Does everybody have scripts on their computer for R that say the first line is set working directory, blah, 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 blah. There's a relatively well-known theoretical ecologist who swears he will come into your lab and burn down your computer if he ever finds that on your script. And his point is that it breaks whenever you give that to somebody else because their directory structure is never the same as yours. So what I've been using a lot of is this here package for R, which is pretty slick. You can just Google it if you want to. But basically what it'll allow you to do is preserve a directory structure within a root directory. So you have some folder that's embedded way deep here. You can make all this anything you want, and that will work on anyone's computer, no matter where they put it in this way. So anyway, and I forgot to run that at the beginning there. Okay, so this is a time series of temperature anomalies from the Northern Hemisphere from the late 1800s to the to current. It happens to be getting warmer, but I understand this is not human caused. That's at least what my administration says. Okay, so back to here then. So there was our temperature time series. So once you have time series objects, one of the nice things about doing that is you can use the logical functions union and intersect to make sure they align. So if you had some that were like this and you union them, right, you'd have one long, do this, there we go, time series. And if you had the intersection, you'd only get the bits in between, right? So you can do that here. You can take the union of those. So this has 1,647 rows, and you plot that using the plot TS again. And here you can see that the temperature time series started way back there, but the CO2 data didn't start till here. But it's maintained the appropriate times x-axis sort of thing, which is nice. If you take the intersection and plot those, now we've cut out about 1,000 rows here, presumably, that were not common to the two of them. And then if you plot those, now the times are exactly aligned. And it would have done the same on the backside too. It will truncate both beginnings and ends. So that's kind of nice if you want to do it. Okay, so back here, we talked quite a bit about decomposition on Tuesday in lecture. Remember we talked about these linear filters. Here's a moving average filter. We talked about this is how we would set one up for monthly data. We didn't talk about this in lecture, but the problem when you have even number of periods is you want this to be balanced. So how can you get K equals 5.5? Doesn't work that well. So typically for monthly data, what people would do is you'd have today out through 5 months, and then you take half of the 6th month on either side. That's all that's doing. So basically, we can create a vector here that's a filter, and then we can pass that to this time series function called filter. And that's just going to pull out the trend. So here, do that. And plot that. There we go. So it's extracted. So this is the trend in the CO2 data. So on average, things are going up. We can then estimate the seasonal effect, right, by just subtraction here. So the idea is that our estimate of the seasonal effect was our observation minus the trend. So we can do that, and we're going to end up with something that's the seasonal effect plus the error. All right, we talked about this the other day. So we go back over here, plot that, and there you have it. Okay, well, we want the seasonal effect without errors, so we have to get the mean effect across all months, and that's all this block of code is doing. It's just asking for the length of that vector. It's calculating the frequency of that, which it knows because I told it it was a time series object. Then I ask it to do some, oh, that's annoying, matrix. This is some integer division just to get the number of periods. So I want to know the number of years that goes, and it will just go through there and calculate that, and then we can go ahead and plot it. So there is the mean effect across all months. So in general, it's warmest in March and it's coldest in July. I'm sorry, this is not the temperature, that's a CO2. It's highest in March and lowest in July, okay, which makes sense. This is when all the photosynthesis is happening, that's when all the respiration is happening. Okay, so we've got a mean monthly effect. Then the next thing we need to do is basically replicate that many times. So that's all this does, is just say replicate this monthly period, the same, or the annual signal, I'm sorry, the number of years we have, and then plot that. So here is our decomposition now. Here's the actual data. There's the trend. Here's the seasonal effect, and that's the leftover bit. Okay. Now is where, has anybody been reading ahead? You could have accomplished all of that with this one command right here. Decompose. So if we do that on our decomposed the time series and plot it, this is it. All it did was add a few more fancier labels, but you get the exact same answer. So that's good. We did it right. Or else we made the same mistake that the people who wrote the function made. But generally, we did it right. Okay. Then the next thing we talked about today in class was this idea of differencing to remove trends or seasons. Right, so you can look through here, and the function in R to do that is diff. And what diff wants to know is what the object is and the number of times to do that. There's also another another argument called lag. So it would tell you what to do. So if we had the CO2 data here, we might want to lag that twice because we had a sort of bit of a quadratic trend there. So let's do that and plot that. So there's our data that had been twice difference. So that got rid of the trend. That was nice because we had this kind of nonlinear increasing trend. But the truth of the matter is now, I think if we yeah, so see, we still have this kind of nasty period in there. And again, this is that funny thing that R did where it was monthly data. So this is 1 year, not 1 month. So what we can do again then is difference these at a lag of 12. But that now this looks much more like white noise. So we've gotten rid of that non-exponential increasing trend and the seasonal aspect. So now we're left with just some nice fuzziness. Okay. Correlation within and among time series. So this was our autocorrelation. I'm going to, remember I mentioned in class how you can do these for the deterministic functions. I'm going to skip that. I didn't put this in here. Okay, we'll skip through this just in the sake of time. So you can run through these in your thing. Yes, Gordon.
Sorry to the one. Is there an issue with order of operations on the twice differing followed by the lags? So you did the twice difference and then you took that object and stuck it in and then lagged it as well.
If you had first differenced at 12, right, you would have got rid of the wiggle, but you can try this on your own, or we could just try it here. You should have seen a linear or an exponential increase after you got rid of the wiggle around it. And then you could twice difference that and you'd be left with this linear stuff. Right, so correct, it does not matter, those orders. But if you did, I think you would get in, think about this for a minute. If you difference once, then difference at 12, and then I don't think that would matter either. We'd have to write it out, but I'll get back to you on that. I don't think that would matter. No, it shouldn't, because they're all linear maps. Okay, so ACF and PACF. So I mentioned, I'm not going to go through all this right now, but I have written out a couple of slightly nicer functions. If you guys want to use those, you're welcome to copy those down. This is cross correlation. We talked about that. So this was the one where I said, you got to be really careful when you put these two together because it wants right here. So this wants the CCF of X and Y, but then it will tell you it's going to evaluate that lags X, T plus K. And so for me, if I'm thinking about a cause and effect thing, that's really difficult for me to deal with. So I set, so this would be the way I would be inclined to call this. Tell it that what it wants is X is what you want is Y, and what it wants is X or Y you want is X. Right? So that's why I do it this way. So there's the two of those time series, which we saw in lecture, and then there's the cross correlation between. So here's sunspots this year. If they're high this year, 4 years later down the road, we think there'll be low lynxes. Okay, and then the last bit of this is the white noise and whatnot. This bit I just wanted to show you quickly because we didn't talk about this in lecture, but here are two different examples of some processes. This is Gaussian white noise, which I added a non-zero mean to, so it's not truly that. Here's a random Poisson variable. If you plot the ACFs of both of those, they both look like this. So here's what we were saying before, the Gaussian white noise is IID. So this is exactly what we expect. There should be no correlations at any other lag. That Poisson is still also sort of a white noise process in the sense that it's a random deviate with no relationship from one to the other. So it also does not demonstrate anything. So it doesn't really matter what you're using for the sort of distributional form there. If it meets a white noise criteria, this is what you should be seeing. Okay. All right, let's see. So that was it. And then this is the last little bit because we'll do the autoregressive stuff on Tuesday. So random walks, again, this is really pretty easy to do, right? Here's the formula for a random walk. It's today is yesterday plus some error term. So all I do here is initialize two vectors, X and W. I start them both with some random normal deviates only because I need to initialize this. I could have called it anything. So X of 1 gets W of 1. That's the way this is working. So here then I run this loop from 2 to the end and do that, and then you plot it, and here's a random walk, and there's the autocorrelation of this random walk with this long, kind of slowly decaying ACF. Something I want to mention to you, because you may see this sometime, is that if you think about a random walk model, these are all the equivalent model, right? It just says yesterday was a function of 2 days ago plus the error yesterday, right? So you do this. If you write all of those out, what you see is that you can really just express a random walk today as a function of all these lags in the past up to time infinity. So if you go through the algebra, what this says is that it's just a sum of all the other ones. So you don't have to do that funny recursion. All you'd have to do is if you had a set of these normal deviates, you just do a cumulative sum of them and you've got what you had. So there's just a demonstration of that if you want. This is the one we simulated before. Here's the new one. and they're exactly the same using either one of those formulations. So sometimes you may see that someone using the Kuhn-Sum argument here, and then that's sometimes people, what the heck is that? But it's just a real easy shorthand way to write a random walk model. Okay, so that's it for today. Tuesday in lecture, we're going to cover stuff about AR models and MR models and ARMA models, and then we'll do this lab stuff at the end of the day. Okay, thank you very much.